on complex numbers. In this lecture, we will discuss a few more problems on complex numbers. First, let us consider the following problem. We are given a complex number omega whose real part is root 3 by 2 and whose imaginary part is half. And P is a set of all positive exponents of omega. Further, we are given two sets H1 and H2 which are defined as follows. The set H1 consists of all complex numbers whose real part is strictly greater than half, whereas the set H2 consists of all complex numbers whose real part is strictly less than minus half. So we are asked the following. Suppose I take a point Z1 belonging to the intersection of P and H1 and a point Z2 which lies in the intersection of P and H2. The question asks for the angle Z1 OZ2 where O is the origin. This is a multiple choice question, so it is possible that more than one options are true. Let us see how to solve this problem. First, we will see how the set P looks like. So to begin with, the set P seems to be infinite, but we will see soon that in fact this set is finite. So we are given that omega is equal to square root of 3 plus I by 2. We will use polar coordinates to write this omega which is equal to cos pi by 6 plus I sin pi by 6. There is an advantage of using polar coordinates here. Since we are interested in the powers of omega, we can use de Moivre's formula. By de Moivre's formula, we have omega to the power 12 is equal to cos 2 pi plus I sin 2 pi, which turns out to be equal to 1. This says that omega is equal to a 12th root of unity. So there are 12 distinct powers of omega. So therefore the set P is omega, omega square, omega cube and so on up to omega to the power 12, which is equal to 1. Therefore, we see that the set P is finite and in fact it consists of 12 elements. Let us now see how the set P intersection H1 and P intersection H2 looks like. Let us represent the points of P on our Gantt diagram. Since the points of P corresponds to the 12th roots of unity, they lie on a circle of radius 1 and the points of H1 and H2 corresponds to the following. Recall that the points of H1 corresponds to the complex numbers whose real part is strictly greater than half. This corresponds to the points which lies on the right of this line, real part of Z is equal to half. Whereas the points of H2 corresponds to the complex numbers whose real part is strictly less than minus half, which corresponds to the points that lie to the left of this line, real part of Z is equal to minus half. Notice that by de Moivre's formula again, omega square is equal to cos pi by 3 plus I sin pi by 3, which turns out to be half plus I square root of 3 by 2. This implies that omega square lies on the line real part of z is equal to half. Similarly, one can verify that omega to the power 4 lies on the line real part of z equal to minus half, and so does also the complex number omega to the power 8, which lies on the line real part of z equal to minus half, and the complex number omega to the power 10 lies on the line real part of z is equal to half. Let us draw all the points of P. Remember, omega makes an angle pi by 6 with the positive x-axis. So omega corresponds to this point, whereas omega square we already drawn. Omega cube corresponds to these points. Omega 4 we have already drawn. Omega 5 is this point. Omega 6 is this point, and omega to the power 7 corresponds to this point, and so on. So we have the point omega 8 already. This is the point corresponding to omega to the power 9. Omega to the power 10 we is already here. Omega to the power 11 corresponds to this point, and omega to the power 12 corresponds to this point, which is equal to 1. Now it is clear that the set P intersection H1, which corresponds to the points of P which lies to the right of the line real part of z equal to half, is equal to omega to the power 12, which is equal to 1, and omega to the power 11. And the set P intersection H2, which corresponds to the points of P that lies on the left of the line real part of z equal to minus half, is equal to omega to the power 5, omega to the power 6, and omega to the power 7. Recall that the point Z1 lies in the intersection of P and H1, whereas the point Z2 lies in the intersection of P and H2. So Z1 can take three values: omega to the power 12, and omega to the power 11, whereas the point Z2 can take three values: omega to the power 5, omega to the power 6, and omega to the power 7. So there are 9 possible values of the angle Z1 O Z2, which are multiple of pi by 6. Let us see what are these possible values. If Z1 equal to omega, then the angle Z1 O Z2 can be, so if Z2 is equal to omega to the power 5, then the angle will be 4 pi by 6, whereas if Z2 is equal to omega to the power 6, then the angle will be 5 pi by 6, whereas if Z2 is equal to omega to the power 7, then the angle will be pi. So the angle Z1O Z2 can be either 4 pi by 6 or 5 pi by 6 or pi. We remark here that the orientation of an angle is very important. Here, by the angle Z1O Z2, we mean that the angle that ray OZ1 makes with the ray OZ2 when we move OZ1 in the counterclockwise direction so that it falls on the ray OZ2. Therefore, if Z1 is equal to omega to the power 12, which is equal to 1, then the angle Z1O Z2 can be, if Z2 equal to omega to the power 5, then the angle will be 5 pi by 6, whereas if Z2 is equal to omega to the power 6, then the angle is pi, and if Z2 is equal to omega to the power 7, then the angle is 7 pi by 6. So the angle Z1O Z2 can take the values 5 pi by 6, pi, and 7 pi by 6. Similarly, if Z1 is equal to omega to the power 11, then the angle Z1O Z2 can take the values. If Z2 is equal to omega to the power 5, then the angle is pi. If Z2 is equal to omega to the power 6, then the angle is 7 pi by 6, whereas if Z2 is equal to omega to the power 7, then the angle will be 8 pi by 6. So possible values of Z1O Z2 are pi, 7 pi by 6, or 8 pi by 6. Let us see among the options given to us which are true. From our calculation, we see that the options A and B are not true, whereas the options C and D are true. So let us mark these options. Next, we consider the following problem. We are given a complex number Z1 whose real part is 3 and imaginary part is 4, and we are given another complex number Z2 whose absolute value is 2. And in the question we are asked to find the greatest and the least values of the absolute value of Z1 minus Z2. We are given 4 options. Let us see how to solve this problem. First of all, we are given a complex number Z1 is equal to 3 plus 4i. This implies that its absolute value is equal to square root of 9 plus 16, which is equal to 5. This implies that the point P corresponding to Z1 lies on a circle of radius 5 centered at origin. Let us mark this point on Argand diagram. So the point P lies somewhere here, which has coordinates 3, 4. Also, in the question we are given another complex number Z2 whose absolute value is 2. Let us write this complex number as x plus iy with absolute value is equal to 2. Therefore, the point corresponding to Z2 lies on a circle of radius 2 centered at origin. Let us denote this point by Q, which has coordinates x, y. Remember, in the question we are asked to find the least and the greatest values of the absolute value of the complex number z1 minus z2, where z1 is a fixed complex number and z2 is a complex number moving on a concentric circle of radius 2. Notice that the absolute value of the complex number z1 minus z2 is nothing but the distance between the points P and Q, where P is a point corresponding to z1 and Q is a point corresponding to z2. Therefore, the absolute value of the complex number z1 minus z2 is nothing but this distance. Now, from the diagram, it is clear that the point Q will be closest to P when P is at the point A, and whereas the point Q is farthest to P when Q is at the point B. What are these points A and B? These points A and B are nothing but the endpoints of the diameter of inner circle passing through the point P. Now, therefore, it is clear that the maximum of absolute value of z1 minus z2 is equal to the distance 5 plus this radius, which is 2, and hence the maximum value is equal to 7, whereas the minimum of absolute value of z1 minus z2 is equal to this distance, which is 5, minus this radius, which is 2. Therefore, minimum distance is equal to 3. Let us see among options given to us which is true. Now, it is clear that the option A is correct. So, let us mark this option. We next consider the following question. For a non-zero complex number z, let this denote the principal argument of the complex number z that lies in the interval minus pi to pi. In the question, we are asked to find the right limit of the principal argument of 1 minus e to the power I theta as theta goes to 0. And we are given 4 options here. Let us see how to solve this problem. Before solving this problem, I would like to recall a few facts on the argument of the complex number. Recall that for a non-zero complex number z, there exists a positive real number r and theta real number such that z is equal to r times ei theta, which is equal to r times cos theta plus I sin theta. This theta is called an argument of z. Since the trigonometric functions are 2 pi periodic, it is clear from the equation star that this theta need not be unique. To make it unique, we define what is called as the principal argument of z. To define this, we fix any semi-open interval of length 2 pi on the real line and define the principal argument of z to be the unique theta satisfying star and that lies in that semi-open interval. In our question, we have given that this semi-open interval is minus pi to pi. So, therefore, the principal argument of z, which is denoted by capital ARG of z, is theta satisfying star such that theta lies in the semi-open interval minus pi to pi. Geometrically, the principal argument of z can be represented as the follows. Let z is equal to x plus iy and p be the point representing the complex number z in the Argand diagram. Then the principal argument of z is nothing but the angle that the ray joining OP makes with the positive x-axis. Now if w is another complex number x1 plus I y1 and q is the point that represents the complex number w, then the argument of the complex number z minus w is nothing but the angle that the vector QP makes with the positive x-axis. So, in this case, the argument of the complex number z minus w is equal to alpha, where alpha is this angle. Let us see how to solve this problem geometrically. We are interested in the complex number 1 minus ei theta. So we have fixed the complex number 1. Let the point represents this complex number. Let q denote the point lying on the unit circle centered at the origin. So it has coordinates cos theta comma sin theta, where theta is the principal argument of the complex number ei theta. Let us see what is the argument of the complex number 1 minus ei theta. So by the previous remark, the argument of the complex number 1 minus ei theta is nothing but the angle that the vector QP makes with the positive x axis. So this is this angle alpha. Notice that as theta approaches 0 from the right side, the point Q approaches to 1 from the upper semicircle. Therefore, it is clear from this diagram that the limit of the principal argument of 1 minus ei theta as theta approaches to 0 from the right hand side is equal to, notice that as the point Q comes to closer and closer to P, the angle alpha decreases from 0 to minus pi by 2. The angle is 0 when Q is at the point minus 1 comma 0. So it is clear that this limit is equal to minus pi by 2. Let us also see how to solve this problem analytically. In the question, we are interested in finding the limit of the principal argument of 1 minus ei theta. Let us denote by f of theta the function, the principal argument of 1 minus ei theta. We have 1 minus ei theta is equal to 1 minus cos theta minus I sin theta. This implies that tan of f of theta is equal to minus sin theta divided by 1 minus cos theta, which on simplifying gives the following. So we use the formula for sin 2 theta. So this is nothing but minus 2 sin theta by 2 times cos theta by 2, whereas the denominator is equal to 2 times sin square theta by 2. We remark here that the denominator is non-zero because we are interested in the limit of f of theta as theta going to 0 from the right, and so theta is non-zero and hence the denominator is non-zero. This is nothing but minus cot theta by 2, which is equal to tan of pi by 2 plus theta by 2. From this equation, it is tempting to conclude that f of theta is equal to pi by 2 plus theta by 2, but this may not be true since the function tan is not injective on the real line. But we can surely conclude that f of theta is equal to pi by 2 plus theta by 2 plus n pi for some integer n. Since f of theta is the argument of the complex number 1 minus ei theta, by the choice of the interval in the question, f of theta lies in the interval minus pi to pi, and also because we are interested in the limit as theta goes to 0 from the right side, theta is non-negative, and we may assume that theta is arbitrarily small. This implies that the possible values of n can be either -1 or 0, because for other values of n, f of theta will not be in the required range. Also, among these values, n is equal to 0 is not possible. Why? Because if n is equal to 0, then f of theta is pi by 2 plus theta by 2, which will imply that the complex number 1 minus ei theta is in the second quadrant, and hence its x coordinate is negative. But whereas it is clear from the equation double star that the x coordinate of the complex number 1 minus ei theta, which is equal to 1 minus cos theta, is non-negative, and hence we exclude the possibility for n equal to 0. Therefore, n is equal to -1, which implies that f of theta is equal to minus pi by 2 plus theta by 2. Therefore, it is clear that the limit of the principal argument of 1 minus ei theta as theta goes to 0 from the right hand side is equal to the limit of f of theta as theta goes to 0 from the right, which is equal to limit of theta goes to 0 from the right of minus pi by 2 plus theta by 2, which is nothing but minus pi by 2. Therefore, it is clear that from the options given to us, the option C is correct. Before proceeding further, I would like to give the following remark. One may wonder why in the question we are asked to find the right limit of this function instead of asking the limit of this function. Let me give the following remark in this regard. Suppose theta is negative, then f of theta, which is equal to this pi by 2 plus theta by 2 plus n pi for an integer n. Now because f of theta lies in the interval minus pi to pi and theta is negative and also is arbitrarily small, since we are interested in the limit of theta as approaches to 0 from the left. The possible values for n are 0 and -1. But n is equal to -1 is not possible in this case. Why? Because if n is equal to -1, then f of theta will be minus pi by 2 plus theta by 2, where theta is negative. Hence, for arbitrarily small values of theta, the real part of the complex number 1 minus ei theta will be negative, which is not the case since the real part of 1 minus ei theta is equal to 1 minus cos theta, which is always non-negative. Therefore, we conclude that in this case n is equal to 0, therefore f of theta is equal to pi by 2 plus theta by 2. Hence, the limit of f of theta as theta goes to 0 minus is equal to pi by 2. From this, we see that the limit of f of theta from the right and from the left are different. This is not surprising since the function argument of the complex number is not continuous on the complex plane. We next consider the following question. We are given a complex number z is equal to x plus iy such that x and y are integers. In the question, we are asked to find the area of the rectangle whose vertices are the roots of the equation z times z bar to the power cube plus z bar times z cube equal to 350. And we are given 4 options here. Let us see how to solve this problem. We are given that z is equal to x plus iy satisfies the equation z times z bar to the power cube plus z bar times z cube is equal to 350. This implies that z times z bar times z bar square plus z square is equal to 350. We know that z times z bar is equal to the square of the absolute value of the complex number z, which is equal to x square plus y square, and z bar square plus z square is equal to z square bar plus z square, which is equal to 2 times real part of z square, which equals 2 times x square minus y square. So, from the equation 1, we get that x square plus y square times x square minus y square is equal to 175. This equation has infinitely many solutions if we allow x and y to be real numbers. But in the question, we are given that x and y are integers. This reduces the number of solutions of this equation drastically. It is not a good idea to write the left hand side as x4 minus y4. Our goal is to find two equations in x and y so that we can solve for x and y. For this, we will factor the right hand side and equate its factors with those of the left hand side. We will keep the factors of the left hand side as it is. Notice that x square minus y square is the smaller factor. So we factorize the right hand side into two factors and equate its smaller factor with x square minus y square and the larger factor with x square plus y square. Now the prime factorization of 175 is equal to 7 into 5 into 5 into 1. Therefore, the only way it can be factored into two factors is either 175 into 1 or 35 into 5 or 25 into 7. The first factorization gives that x square minus y square is equal to 1 and x square plus y square is equal to 175. This implies that x square is equal to 88, which has no solutions in integers. So we discard this factorization. The second factorization gives that x square minus y square is equal to 5 and x square plus y square is equal to 35. This implies that x square is equal to 20, which again has no solutions in integers. So we discard this factorization as well. The third factorization gives that x square minus y square is equal to 7 and x square plus y square is equal to 25. This implies that x square is equal to 16 and hence x is equal to plus or minus 4. This in turn implies that y square is equal to 9 and hence y is equal to plus or minus 3. These are the four integral solutions of the equation 1. These four solutions correspond to the four vertices of the rectangle whose vertices are 4, 3, minus 4, 3, minus 4, minus 3 and 4, minus 3. Therefore, the rectangle that we are interested in is this one. Let us label the vertices of this rectangle as A, B, C and D. Now it is clear from this diagram that the area of the rectangle ABCD is, so its length is clearly 8 units, whereas its width is 6 units. Therefore, area of the rectangle ABCD is equal to 48 units. Therefore, among the options given to us, we see that the option A is correct. We next consider the following question. Let omega be a complex cube root of unity which is distinct from 1 and a fair die is thrown 3 times to obtain the numbers say R1, R2, R3. In the question we are asked to find the probability that omega to the power R1 plus omega to the power R2 plus omega to the power R3 is equal to 0. We are given 4 options here. Let us solve this problem. First of all, I would like to recall that the probability of a given event is the total number of possible events divided by the total number of possible outcomes. Here, the set of all possible outcomes, let us call this as S, is the set of all ordered pairs R1, R2, R3 such that since each Ri corresponds to the number that we obtain on the die, they lie in the range 1 to 6. Therefore, the total number of possible outcomes is equal to 6 to the power cube. Let us see how the set of all events looks like. Now, the set of all events is, let us denote this by E, the set of all ordered pairs R1, R2, R3 that are inside S such that omega to the power R1 plus omega to the power R2 plus omega to the power R3 is equal to 0. Therefore, we are interested in finding all possible values of R1, R2, R3 so that this equation omega to the power R1 plus omega to the power R2 plus omega to the power R3 is equal to 0. The basic equation satisfied by omega is omega square plus omega plus 1 is equal to 0. It is clear that this equation is still true if you multiply this equation by any powers of omega. Moreover, since omega cube is equal to 1, we can multiply any of the terms of this equation by omega cube or its power to get another sum of 3 powers of omega that add to 0. For example, if we multiply the term omega of this equation by omega cube, we get omega square plus omega to the power 4 plus 1 equal to 0. Or remember, we have to interpret 1 in this equation as omega cube or omega to the power 6. Therefore, multiplying 1 by omega to the power 6, we get another equation, omega square plus omega to the power 6 is equal to 0. Therefore, among the permissible values from 1 to 6, we see that one of the Ri has to be either 1 or 4. The second Ri has to be either 2 or 5, while the third Ri has to be either 3 or 6. Therefore, there are two possibilities for each Ri, and since they are distinct, they can be permuted among themselves in 6 ways. Therefore, the cardinality of the number of events is equal to 2 cube into 6. Therefore, the desired probability is equal to cardinality of E divided by cardinality of S, which is equal to 2 cube into 6 divided by 6 cube, which is equal to 8 by 36, which is equal to 2 by 9. Therefore, among the options given to us, the option C is correct. We next consider the following question. Let C denote the set of all complex numbers and let S be the set of complex numbers such that Z bar is equal to Z square, where Z bar denote the complex conjugate of Z. Then in the question we are asked to find the cardinality of the set S, and we are given 4 options here. Let us see how to solve this problem. First of all, recall that for a given complex number, Z is equal to x plus iy, its complex conjugate Z bar is given by x minus iy. In the question, we are given that S is the set of all complex numbers such that Z bar is equal to Z square. This implies that x minus iy is equal to x plus iy the whole square, which is equal to x square minus y square plus I times 2xy. Therefore, comparing the real and imaginary part of this equation, we get that x is equal to x square minus y square and minus y is equal to 2xy. Let us label this equation as 1 and 2. Now, from the equation 2, it is clear that either y is 0 or x is equal to minus half. Suppose y is equal to 0, then from 1 we see that x is equal to x square. This will imply that either x is equal to 0 or x is equal to 1. Therefore, in the case y is equal to 0, we get two solutions of the equation star. Now, suppose x is equal to minus half, then again from equation 1 we see that y square is equal to x square minus x, which gives that y square is equal to 1 by 4 plus half, which is equal to 3 by 4, and hence y is equal to plus or minus square root of 3 by 2. Therefore, for x is equal to minus half also we get two more solutions satisfying the equation star. Therefore, the set S consists of 0, 1, which corresponds to y is equal to 0, and minus half plus or minus I times square root of 3 by 2, which corresponds to x is equal to minus half. Therefore, we see that the cardinality of S is equal to 4. Hence, among the options given to us, the option C is correct. This finishes the second lecture on complex numbers. Thank you.